Okay.
Perfect.
All right. Great. Great.
Thank you.
I've got so much on my desktop. I guarantee I'll get lost tonight. Okay. So once again, folks, thanks so much for coming. We've got over 30 folks in the room, and I'm sure people are from different parts of the world. So thank you so much for coming at this time. Uh, and once again, this is going to be a conversation on the different methods and hyperspectral data analysis, hyperspectral imagery that's used for the identification of minerals. Hyperspectral imagery is not new. It's been around with us for several decades. It originally was conceived for the purposes of identifying and quantifying, exploring mineral resources on Earth. It's being used in other planets now, moons, and even asteroids. Um, and so it's a really neat tool in the geoscience world. But guess what? It's actually magnitudes larger in other industries. It is growing at an extreme rapid rate in the natural resources as far as agriculture. That's the largest scope right now. It's a magnitude larger or more. Okay, it's growing rapidly, and if there's time, I'll be happy to shed a little insight with that because I know a lot of us in the geological world, geoscience world, sometimes we have to go into things like water or land use sometimes depending on consulting. So there's some aspects that let's say overlap. At the same side of the coin, it's also growing massively in biomedical. And for the main reason is that, which I will share a little bit today, I spoke a lot about it last during the previous lecture, but due to what you can actually see, I like to use the phrase seeing the unseen. Um, it's a great way to explain it. Our eyes cannot see most of the hyperspectral world in those wavelengths, but these tools can. So with all going forward here, there's going to be a little tiny review of what we previously discussed. There are many satellites and growing in orbit around the Earth that are capturing um, all parts of our planet, from coastlines, oceans, to islands, different continents, looking at anything and everything. Right now, it's growing at a rapid rate. Looking at what hyperspectral, in comparison to some of our previous tools we use, the popular Landsat system, as you see here, this popular Landsat system, these areas here are bands. Think of this as like bands, okay? So on the left side here, which you can't see my, hold on the left side here, this is our blue, green, red, right? Blue, green, red. We like to say red, green, blue, but it's inverted when you look at the wavelengths. So blue is on this side, uh, green in the middle, red. And as we go further, we get into the infrared. So Landsat are these bars, okay? But with hyperspectral, it's a continuous signal, that a continuous observation along the wavelength from visible light to infrared, near infrared, and beyond. Okay. The importance in that, the importance in that is there's a lot of information that is located here and located here, and so on. And part of this, or should I say, the most important part of this is that hyperspectral, what it's really doing, what it's physically doing, is that it is observing components in the subatomic scale. Okay, it's a reflection. Okay, it's just like Lancet, it's reflecting back into the sensor, but it's a response based on the chemical and physical components that make up that substance. So, as you already know, geologists, that there's a considerable amount of information that's in geochemistry that has to do with the chemistry, that has to do with the physical structure of these minerals. So as a result, and we use hyperspectral, we're able to see the we're able to see a specific signature for that material. And that's the beauty of it, which is one of the reasons why it's being used in so many industries. You know, just think about water quality, think about solid waste management, think about food processing. The list goes on. And the instruments that are used in this, of course, our satellites are these relatively large size instruments that are used in orbit, that are flying around there. They can move, you know, they can position themselves and so forth. They've been around, some of them have been around for quite some time. The projects have done very well for themselves. So there are iterations of them, like Landsat. I think Landsat is on to number 9 now. Last year or the year before, they launched number 9 for Landsat. Hyperion or Hyperion, which is one of my favorites, recently shut down, but it was in space for almost 20 years, or not 20 years. And it was able to capture a lot of information, which is what we're going to look at today. Now, due to the fact that we're able to miniaturize this equipment, you can put these on airplanes, you can put these on drones, which drones is a massive industry right now. The only big problem with hyperspectral cameras is that hyperspectral cameras are very, very expensive. So looking at these cameras here, some of them in particular can fit. They can fit in your palm of your hand. And you ready for this? These cameras can be in excess of $50,000. Okay, the really good ones. And I mention that because the ones that are accessible, that are in the sub $20,000 range, those only see up to, they're configured to operate in the near infrared or red edge that some people like to use. So you're going to miss this component, and this component becomes important when we look at minerals. And I'll go more into that a little later. So it's at the point where it's very expensive to do it, but you can actually manufacture cameras. If you're a pretty good electrical engineer, electrical person, you could put together enough components and make a makeshift camera. You can do this. It'll probably cost you definitely under a few $1,000s. One last thing I may have mentioned, I think I did mention water quality. Yes, with hyperspectral, you can actually, depending on the depth, water, the bathymetry you're dealing with, you can actually image below the surface of water. So what does that mean in the context of shallow water environments, and in the context of oceanography, in the context of minerals on the bottom of the ocean floor? Okay, you see where this is going? It's here's an example of someone out in the field. This person's in the field and they're using a hyperspectral camera, high grade camera, and they're imaging the rocks that are out in the that are outcrop, and collecting that information on site, where they're using that to build what we call reference data. And I speak about that. This is a new one we have here from the previous lecture. And someone please help me later on with the pronunciation. I have to make sure I get this one right. We never discussed this in my mineralogy class, but this is a very, very important rare earth, what we call REEs. It's not an element, it's a mineral, bastnäsite. I could be pronouncing it wrong, but it's extremely important because we got lanthanide, we have yttrium in here as well. And it's a carbonate. And we're going to look at this one much more closely today. Are there any questions? Any questions? Hands up. I see some chat. Okay. Going on, moving forward. So when you take a hyperspectral image of that mineral, this one here in particular was acquired in, I think this one is acquired in the site that we're looking at today. But you can see here the spectrum as it is a continuous spectra. We have a hot spot here, we have a hot spot here, and we have a hot spot here. Now, do realize that the visible spectrum is here, going into the near infrared. Then we're moving into further deeper into infrared and further down the spectrum. And these are in, I want to say nanometers. So you can see how this is this is what we would call a signature for this mineral. If we looked at other minerals, they would look differently, but they all have a unique pattern with them, and that is right around here, and of course a little further back, but here and here, you see these dips? These dips are the result of water vapor in the air. So you already know that when any kind of electrical, electromagnetic, anything that goes into water, when it comes into contact with that water, it gets attenuated. So what's happening is that you're getting a signal loss. Signal loss is what creates these dips that are here. And this is very important because when you're processing, collecting this information, which we're going to see now going forward, but you're not going to want to utilize that information unless you're looking for something specific that's within that range, and depending on the sensitivity of the instrument that you're using. And that takes us to this portion here, which these are, when we look at the steps going forward for our data preparation and processing, the hyper ion, which is the instrument of choice that we're going to be discussing today, what makes it so special, made it so special, is that it subdivided that continuous spectrum into 242 bands. Not really 242, which we're going to talk about, but that's what the capabilities of the instrument are. And with Landsat, remember, Landsat has eight bands, right? Red, green, blue, near infrared, infrared, and I want to say there was also another infrared, and then there was a panoramic, depending on the instrument, the Landsat instrument, at different resolutions. But with the hyperion and some of the other ones, hyperion I mentioned because hyperion has the most. There are others that have 20 bands, 40 bands, and there are many different companies out there that are producing their own satellites to do exactly what we're discussing, but more in the agricultural world or in hazards or in the context of climate change when one's looking at fugitive gases. They're really going after carbon dioxide fluxes, they're going after methane fluxes and the type. But what goes on here when we process this hyperspectral data, these are what we would call bad bands, and they're classified as that unless you need something specific. This one here, 1 to 7, is not illuminated. The 58 to 78, these are bands. Okay, they're subdivided, very narrow, very narrow bands, and you can see with these wavelengths. See, this is wavelength. This is the size of the sort of like the size of the path of the scan. Okay, and this is a picture, so I can't move it. But what you have here, these are the wavelengths. Okay, in nanometers, and you can see that those wavelengths are roughly about 10, somewhere between 10 to 11 in separation. Okay, so very small slices that can be utilized in breaking up those bands, breaking up that continuous spectrum. So there are components that can be taken out for filtering, for processing. There's information that you're not going to need, so you take them out. In this case, this is the basic starter for processing our data. We're removing those water absorption bands, okay, where that attenuation takes place. So you go in here and you highlight those bands. This particular package here is Envy. There are many of them out there, which today I'm going to demonstrate utilizing Envy as well as IDQ Pro, okay, which is a new system, which we'll talk about. And you remove these, and as a result of removing these bands, you have a much smaller file. Because one of the big things about hyperspectral is that you're talking about, instead of having 7 layers, you have 200 plus layers. Okay, So your file size is not going to be, say, 100K or 100 megs. Your file size is going to be a gig. Okay, so Landsat is 100 meg. Hyperion is 1 gig for file size. Okay, so for folks that are looking at very large data sets, okay, large continental scale data, large regional data sets, you have something that is, when it processes, it's going to take a long time to process, and you're probably looking at putting it in a cloud, running it from there, because of the amount of data that you have, and you're going to have to store this at some point, because you're going to be, it's not just a one shot thing. It's sort of like processing geophysical data, where you're tweaking as you're going forward. So there are many different iterations that you'll process going forward to find the best set of attributes as you hone in your signals. Okay. After we do our bad band removal, we have to remove a lot of the noise. And one of those aspects of removing the noise is something called MNF, or minimum noise fraction. And what it does, it's a comparison of the signal to noise ratio. It computes the statistics from this with the attempt of removing the noise from the data set, because you have all of these different channels, and you can get noise for whatever reason, one or another. And you have so many bands to choose from. And depending on what you're looking at, what you're observing, you can select those bands, which is different from what we would see in the traditional Landsat. In Landsat, you have, a band 4 or a band 5, and you're doing some band math, and that's it. Whereas with hyperspectral, you have basically a couple of bands that you can work with when you're performing the band math for whatever you're trying to extract from this raster data set. So in this case here, this is using the IDQ Pro that's produced by Spec-Q, and this is one company that I'm helping with the development process. It's a relatively new software package. It's still under heavy development. One of the nice things is that I'm using this, and it does some things quite nicely. One of the things that it does quite nicely is it has a maximum noise fraction. And I'll show you, I'll perform a couple of steps with you so you can see this. But what we have here is that of the same file. Let me bring that file up here so you can see this. I need to reshare my page. So in the here's the envy. You see it? Okay, here is the envy, and some folks might recognize this. If you cannot see this, please say so. But you see this line here? This is a road, and this is U.S. Highway 15. Highway 15, California is on the west side, and on the right side is Nevada. So I think it's not here. Can you see this? No. I don't think you can see it. Oh, you can see it? Okay, great. So so what this is Mountain Pass. And Mountain Pass, some of you folks who've actually driven from Los Angeles to Las Vegas, you pass right by Mountain Pass. And Mountain Pass is right at the very top of Mountain Pass is a large mine. And this mine is they're mining those those rare earth elements. It's a strategic national operation network where it's one of the largest mining operations for rare earth elements in North America, and for good reason. Not to go into the geology of this, but you could see how the rocks here are totally different colors because they are different rocks. This side, it's these are those carbonates which are thrusted. It's a relatively low angle thrust fault that's coming up here, and that outcrop are those rare earth elements, those minerals, basidiosite, which is exposed here at very high concentrations, and it's being exploited in this area. So for this exercise tonight, I bring this hyperspectral coverage, which I'll show you how to find it as well as others today. And this one is that was done on the ENVI system. The next one we have, I took it from there into ID Cube. So here in ID Cube, what we have is, it doesn't want to give me the whole screen. Show more windows. So what I did, I took the file and I brought it into ID Cube because it does a very nice job. ID Cube, first of all, just let folks know, ID Cube is was originally designed for a lot of the biomedical industry, but it's now being adopted to parlay into the other industries, like I mentioned, agriculture, as well as in minerals. So it has some very nice mathematical algorithms in it that allow you to perform the same task, but it does it from a different way. And in my opinion, it does it in a very nice way, which is why I'm sharing this with you. I just want to show you the right thing here. So a little bit, so let's just show you this one. We'll just go step by step. So in this case, in this case here, um, you put the system in there, and what it does, it makes the attempt to minimize the noise that are remaining within the remaining spectral bands that you have. This was after I did the band removal. I removed it from 242 bands, and after the removal process, it went down to 161 bands. So that's a significant amount of data reduction, which is part of the processing steps that you have to go through, as well as cropping your area because you don't want to use the entire length of the raster. You usually only need to use portion of the raster, so you also want to provide a spatial uh, um, delineation as well, and that's what we've done here. So this is only a fraction of the size of the original. And what it does, it takes us into a set of algorithms. One of them is a principal component computation for orienting and reparameterizing where you have the greatest signals, okay, where the greatest signals are in all of your in a majority of your bands. You're not going to look at all 160 bands. I think I selected somewhere between 20 to 50 bands, and it looks at the top 20 bands, let's say, and of those top 20 bands, it picks the best ones that are ranked, and those are the ones that have the highest signal to what you're looking at. And then what takes place after that, it provides you with a very nice feature here. 1 second. Provides you with a very, very nice feature, which show you on the screen. it gives you this principal component analysis grid where you can actually physically, you can move this to identify which scales or which axes has the largest coefficients in your principal component analysis. This one is 3. So I'm looking for which ones are the largest, which has the largest amplitude, which is this one here that sticks way out over here. And that particular one, I'm hoping is my bassinet site. Okay. And with the output file, with the output file, as you can see here, the eigenvalues, that's what they call these axes, these eigenvalues, very small signal as we go to the entire data set. And as we get to just a very few with very high signal. And that's what we're looking for. That's how you know that you're on point with at least that particular file, that there are, after the principal component analysis. With this, I would say there are only 1 or 2 that are very, very high values. All the other ones are, their contribution is very little. And that's what I expected to see. Now, once again, this is still back into the IDQ Pro, and let's make the move with this. I stopped it where we can process this on site. So this is where we are at the final stage of the MNF after the principal component analysis. One thing I do have to say is that there's something going on with file over here where it's I don't know what this is. It's either noise or something on the side of the image that's causing a problem, some anomaly. But one thing to point out is, you see this yellow here? This yellow here is actually this cluster here, and this cluster is where the bassinet is located in this rock. And I've been looking at the mountain pass for quite a while, and at least from what I see from the sky, there's a considerable amount of minerals, of bassinet mineral, that's not just exposed at these rocks, outcrop, but part of the as it's being eroded and run and the runoff as it flows downstream, because in that part of Nevada they get, even though it's only a couple of times of the year, but they have extreme rain events that huge volleys of water of those intermittent streams come to life, and it's washing this stuff as it's eroding, because they also get freeze and thaw. There's a lot of that goes on during a part of the year and that area. So that mineral is deposited all over the place in varying concentrations, of course. But this is what shows up in the hyperspectral, and this is what we're seeing here. Okay. So let me show you. Let's go forward with this here, and let's see if we can get it to go. So once again, we're going to be pulling. This is the program live. This is the live program here. And what we're going to be pulling now, we're going to be pulling this class here. So let's see if this works. And what it does, it's now taking, and it's it's basically providing us the brightest, is giving us the brightest color for that uh, principal component, for that, I'm sorry, for that cluster of data that it identified through the principal component analysis. Is providing those values in the raster data set, which is what we have here. So these are the results. Resulting image shows the overlay image of selected class in bright random colors. The total area covered by the class is provided under the image. Select a different, select a different, the resulting image, the total area covered, and says select a different number of classes and a different K meta-nodes, distance, metrics, and apply again. So you can, this is part of the routine where you can do this several times. If we had something more classification, if we were looking at other minerals and associated. So so yes, we're looking at bastnaesite, but what would if we were looking at some of the other associated minerals? We could put that information in this for in part of our classification scheme, so we could identify more than just one. In this case, we'd be able to easily identify another 3 or 4. Okay. So let's just press OK here. And this image here, this cluster here, that's the area of this space. And I want to say this is in square kilometers. So it's pretty big. And what is, of course, what does it really look like? And I will show you, in this case here, you would want to, export that view, because you could do that, export it, and then there should be some other processes. And if it's not in the application, it will be in the application later as it's further developed, because I am making comments as we go forward. But you'll be able to have a transparent area around here, so you could have a gamma, so that this would be transparent. And you could take this image, and it would be geographically, it would have the geographical corrections already applied to it, and you'd be able to just drop it into your GIS, onto your geologic map. That's what you want to be able to do. So let me show you outcome of what we have here. Looks a little nicer, doesn't it? So this is the same image, the same hyperspectral image. This is the this greenish color is the color in question. That's the color in question. This is the mineral in question. And as you can see, you could see how this is, it looks like it's running off, and it is as it is eroding, going through the mechanical weathering and chemical weathering. But the mineral overall is still part of the runoff here. And it's in of course, highest concentrations here where that thrust is exposed. But it's also, as it is weathering, it is being deposited down grading, because this is a mountain. This is about 9,000 feet, and it's a pretty steep gradient on the other side. So as time goes on, this is what is depositing down gradient on this side of the slope. It's very, very interesting. At this point in time, we can have a quick Q&A while we go to the next step. Are there any questions?
All right. Do you see? Or if anybody wants to raise their hand, we can.
Yeah, someone had a question about the dimensions of the XY axis. Yes, that's really good. The resolution of each pixel is 30 meters. Okay, so, and the number of pixels, I'll tell you right now, I should know this right off the back, but I'm going to give you the exact numbers.
Okay, we have a hand raised. So Michelle Lee.
Hi, Michelle.
Michelle?
Yes,
Okay.
I went
We
ahead and
can-
just put into the chat.
Well, you're welcome to ask too if you want.
Holy
You're
smoke,
unmuted.
we have a lot of questions here.
Okay.
Regarding the XY axes, I will get that before we close today because I have this information. It's a very small because it's a very small it's a very small area that the hyperspectral maps. And okay, 256 times 30. That's 7,680 meters across. And it's 1,000 and it's 30,000 meters in the y-axis. That's the dimension of the crop. So 7680 meters by 30,000 meters. And next question, what is the cost of the software? Frank, the cost of the software is about, there's a free version, which is a viewer version, which I'm going to show you today, how to use the system in a viewer version. So folks, type in countries that you want to look at, some geology. I'll show you how to find it. I'll take the first 5. Okay, so go ahead and type them in chat, the name of the countries, and we'll see what we can find. So I think the software is about $1,400. I think it's about that. I could be wrong, but I think it's about $1,400 for a license, and that would be I'm almost certain it's a temporal license. It's not all it's not a perpetual. What band ratio is used to identify the minerals? The band ratio. That band ratio, I don't have that here, but I can put up. Band ratio. I will get that. And the next one, next question is,
I think they're giving you some countries to look at.
yeah, we can't do, I don't, we might be able to do islands, but I doubt that, but let's see. Okay, I'm gonna bring it up right now. So take a look, I'm gonna share the screen here. So this program, one of the programs that we use, this is Earth Explorer, and you see the domain, right? earthexplorer.usgs.gov. Really it's a straightforward program. So looking at our first, what was the first location? Sierra Leone.
Yes.
Okay, so Sierra Leone. I'm looking at just using the Hyperion, and notice what I do. This is the coverage map. So we'll see what's there. So as you can see, there's the world map. There's quite a bit, it's not bad. You can kind of tell that somebody's looking at specific things. But let's see, Sierra Leone is right here. So yes, so we got a couple places in Sierra Leone, not a lot, but there are a few places here. Any place in particular you want to look at? This doesn't look like a whole lot going on there. Not a lot going on there. I can tell you right now, there's something big going on right here. You see that? That looks like a mining operation. But let's look right here. So what I'm going to do, if I want to get this strip, if I want this strip, I go to search criteria. The easiest way to do it is press circle, okay, and make a circle. Make a dot right there, and just to make sure I get it. And kilometers. All right. So the most important thing is the data, is the date. I don't know what the date is for this. It's a very wide date, but from a geologic perspective, it really doesn't change, right? So if I just go to, let's say January 1st, and let's say 2000, let's see what's there, and 12, I'm just punching numbers here, folks. 2016, cloud cover. We're going to get whatever's there, right? So that's all that's going to happen. And we're looking at all months. On some cases, you want to look at temporal data. Select the Hyperion. And we have there are 4. It was shot 4 times, which that means to me they really wanted to see this. Right? 1, 2, 3, 4. So out of these 4 images, 2 are good, 2 obscured. Right, so these are the images right here. And how do you get them? The easy way is you press the download option, right? What pops up? These are the options you have. This is a GIS ready JPEG with a world file, allowing you to put it in any kind of GIS platform of what that image looks like. This is just a simple JPEG for publishing. This is L1T. L1T is a GeoTIFF format. So it has some geospatial, it has some correction, it has some what we call geographic information, a geometric correction in it, so it's rectified. But it does not have it does not have all of the corrections that were done on the data set. If you want something that's in GeoTIFF format that's fully corrected, atmospheric correction, your 2 choices, your 2 options are this one here, L1 GST, and this one here, L1R. Now, do realize in GeoTIFF format, it's going to give you a bunch of TIFFs. It's going to just give you a bunch of TIFFs, a couple hundred TIFFs. In this case, here, HDF is going to give you the header file, which is a very, very small file, and it's going to give you the hyperspectral cube. It's not a cube, it's a rectangle, a big, thick rectangle. So that's what it's going to give you. And depending on the tools that you use, so if you're using QGIS, you're going to be maybe looking at this one. If you want to use this one in QGIS, you're going to have to break those bands down so you can use them as individual bands in QGIS, and then create a virtual band or do whatever band map that you might want to perform. In NV, Rasterio, which is a free program, in IDQ Pro, works perfectly fine with it. IDQ Pro works very well with this. NV works very well with this. ERDOS should work pretty well with this too. More questions?
There's one that says, are there preset bands that specifically look for specific minerals that are macros? Also, where do you get the data sets from?
This is where you get the data. This is the data set here. The hyperspectral data set. It's here. So you download them. So I will download this right here. Right, so you see how fast it is. My connection is not the greatest. It's not a Google Fiber connection, nothing like that. This is Comcast, which is about half the speed. About half the speed. You could see this one is taking about 10 minutes. That's typical. It's only 214 megabyte, not very large at all. Not a lot of data in this file. Some of them tend to be much larger than this because they have much longer set of rows. Someone also mentioned, go ahead.
I'm not sure if you might already answered this one. Is USGS mineral database used for identification?
Is the USGS database?
Mineral database used
Yes.
for,
Yes, I will show that. Those are what we call our reference data, right? So I'll go back to that. Hold on a second. Can you see this?
we see the screen that has the download option.
Do you see this? Do you see my file now?
No, I see that it says that zip file down there. Oh yeah, you might have to stop sharing and then reshare.
Okay, so
Okay.
this
Yep.
is what's inside the zip file. So it has, this is the main file, the hyperspectral cube. Okay. This is the header file, which is like the file that points with the metadata that points to that file. And let's see here. This file here, MET, I think is used in atmospheric correction, I think. But what's important here is you see this letter, these letters and numbers here. That means this is like a stamp, an identification stamp for that file that has to do with the satellite that took the information. So EO1 is the Earth Observer 1, which is the name of the craft. And then after that is the sensor is Hyperion H. After that is the target path. So 201 is the target path. The next number is 054 is the target row. So if you know the path and row, which is unique for that location on Earth, you just tell any satellite that you're looking for that path or row, and it'll tell you if that satellite has information for that location. What comes next, 2004, this is the year of the acquisition. 006 is Julian date of the acquisition. And the last one here is 110, which is Hyperion, and ALI, which is another one of the instruments on the Earth Explorer platform. And the PZ is I don't know what was that. It has to do with the scene length. Okay, scene length. So it's a partial scene. Remember, it's a small file, partial. And what was the ground receiving station, whatever Z is, where the data came in. I'm not sure what the FG is. It has to do with another metadata file that's in here. And the aux file, which is pretty big. The aux file. It's some sort of, it's an auxiliary data set file. It contains data layers for the spectral information, the bandwidth, the gain, flag maps. It's all part of the processing information. So if somebody went back in and reprocessed this, they would have information on how it was processed. And I can tell you right now, in my experience, that's not uncommon for the federal government to go back in, or some contractor to go back in and reprocess data. I think the new Landsat satellite that's up right now, the first year they had to reprocess everything all over again for whatever reason. I don't know. We had another site, spatial resolution data. I said it's 30 meters. Someone asked about St. Croix, Virgin Islands. No problem. It's real easy to start this over again, clear the circle. And Virgin Islands.
I see that Frank Sims has his hand up. If we can see if he has a question, I can
Yes.
open his mic.
Yep.
Okay. Frank, did you have a question?
Yeah, can you hear me?
Yes,
Yep.
I can.
Yeah, it was sort of I had those two questions, but when I was talking about the data sets, the question I was trying to get at is when you went to the Earth Explorer, you get what you get. But what if I want something more? Like, what if I need somebody to, like you said, Hyperion came down. So is there a satellite system that can be used by contract to gather the data?
Absolutely.
That's
Absolutely. There are other ways of doing this. And one of those awesome ways right now is drone, right? There are numerous drone contractors that you can hire to shoot your hyperspectral data.
Okay.
They will charge you probably, after you see, it's going to cost you several $1,000s to capture. But depending on the size of your project and what you're looking at.
Yeah.
Kind
of like Aeromag or anything else. Just whatever geophysical remote sensing. Okay. But then the other question I was asking really was like, so in the software, your ID cube.
Yes.
So is there like pre-programmed, say there's specific minerals that have a pre-programmed filter? So like I don't have to go in and figure out which bands they are. I can just click on carbonate, or I can click on lanthanides, or I can click on something where, like an XRF machine has a series of macros, and you click on what spectrum you're looking for, and then you run it through the XRF machine, and it's looking for those minerals and concentrations, right?
Yeah. And I can only assume that there should be companies that offer that, because it's what's already offered in the agricultural world. So in the ag space, NDVDI, NMDI, looking at soil moisture, looking at leaf health, the phenology of plants. There's so many attributes that are already in play, because those are pretty straightforward band ratios, that are used in multi-spec. So
I mean,
would
is there like a
only
list? Is there
assume-
like a list of like these are the bands you use? Like, is there a preset list where you can go look up like a kind of like if I was starting off, I'm a new person, I don't know which bands equal what, but is there like a published place where it says, okay, when you look at these bands, these are the ones you're looking for, whatever,
Yeah. So let's see, we call that's the spectral library. Okay. So there's spectral libraries, I want to say Eco Stress as a library.
Who is that again?
Eco Stress. I'm sharing my screen.
Yeah, I mean, the only reason I'm asking this is because if anybody's new to this and they're running through all this stuff, they're gonna get data, but then they don't know what to do with the data.
Oh yeah, it's there's plenty. You're gonna be overwhelmed.
Yeah.
There's this Eco Stress Spectral Library. This is part of an instrument that's on the space station, and they were really going after a lot of coastal scenes. but it's evolved way beyond that. And I'm almost certain you can get minerals here too. Matter of fact, you see this here? This is lunar information. So, you know,
Oh, wow.
I worked on a project where I looked at minerals on the moon. That was about 2 years ago. But there are many attributes. You can see it is 30, there are over 3,400 spectra here. So if we just go to minerals, right? And let's take a look at the minerals, right? Olivine, quartz, wallenstein. Here's the next one. Type. Right? So if I click on view plot, this is the spectra for this mineral. And you would take this file and you would put this file in your hyperspectral processing package, and you can tell it to look for these particular points. Now this one here, wavelength, this is in micrometers. So being in micrometers, this has nanometers. This would be like 0.1, this would be 1, something like that. So depending on the application would determine whether or not you'd be using hyperspectral or whether you'd be using multispectral, depending on the mineral. So there's just an overwhelming amount of information available at your fingertips.
Thank you.
You're welcome.
All right. Well, I guess we've used up our hour. It went by quickly, and like you said, Troy, we'll probably need you to do another part. So I know you said there's a lot of information
Yeah.
that you can present on this topic. So we really appreciate that.
Absolutely.
And for you coming back. And
yes, and on the next one, I'll be happy to take it further. And what we can do is, because I'll have more time, we can look at maybe we could ask folks up, in advance for certain
Sure.
areas that they might be interested in. And
Okay.
and I'll have some work, what we would call a pipeline. I could do a pipeline on IDQ Pro and one of the other applications as well.
Great. Great. All right. Well, thank you, everyone. The Texas section has a webinar every third Tuesday. And so watch that on the calendar for upcoming topics. And we hope to see Troy again soon on another webinar for us. So thank you, everyone. And thank you, Troy. We really appreciate it.
You're welcome. Thanks for having me.
Good night, everyone.